All right, let's look at another example. I want to find the first four terms of the sequence given by an equals 4n plus 3. And then we want to answer is the question arithmetic. So when we're looking for the terms of the sequence, I'm just going to replace n with the term I'm at. So in this case, we're going to start with a1, and that's going to be 4 times 1 plus 3. That's 7. A2 is going to be 4 times 2 plus 3. That's 8 plus 3, which is 11. A3 is 4 times 3 plus 3. That's 15. A4 is 4 times 4 plus 3. That's 16 plus 3, or 19. All right, so is this sequence arithmetic? So this sequence keeps going. And what do you notice if we look at the difference between terms? 11 minus 7 is 4. So what are we doing here? We're adding 4. And to go from 11 to 15, we've added 4 again and added 4 again. This certainly looks to be arithmetic, although the formula doesn't quite look like our arithmetic sequence. So let's try rewriting this. So we're adding 4 each time, so our common difference here is 4. What was A1? A1 is our first term. That's over here, which was 7. And so the formula says that an is a1 plus n minus 1 times d. Let's plug those numbers in. I get 7 plus n minus 1 times 4. Let me distribute that 4. I get 7 plus 4n minus 4. And 7 minus 4 is 3. So that becomes 4n plus 3. And that's the formula that we have up here. So this formula up here is just a cleaned up version of the arithmetic formula. Okay? Let's look at another example. Here we've got a pattern that we're looking at. So we don't always have to be looking at just numbers, right? But the pattern here is going to involve the number of matchsticks. So what's happening here? In the first figure, I've got 4 matchsticks. In the second figure, I added on 3 matchsticks for a total of 7. In the next figure, we're going to tack on 3 more matchsticks to make 3 of these boxes. That gives us a total of 10. And then again, we've tacked on 3 more, so 13. Again, this is an arithmetic sequence. And this is one that we've seen before, right? We're going to start with first term 4 and common difference 3. All right, the second special type of sequence that we want to consider in this section is geometric sequences. So the idea with geometric sequences is that each successive term is gotten by taking the previous term and multiplying it by a fixed number, which we're going to call the common ratio. We can also figure out what that fixed number is by looking at the ratio of successive terms. So that's where that ratio is coming from. So if we look at the sequence 2, 8, 32, 128, and so on, this is a geometric sequence because if we look at the ratio of successive terms, we get 4. So if I take 8 over 2, I get 4. If I take 32 over 8, that's also 4. 128 divided by 32 is also 4. Okay? If I'm moving from the right to the left, if I think about going from 2 to 8, what am I doing? I'm multiplying by 4. Okay, so that's our common ratio. All right, so let's try answering some questions about this sequence. So first of all, what is the third term of this sequence? Well, I've got A1 is 2, A2 is 8, so A3 is this third term. A3 is 32. Again, I want to ask you, what's A10? Well, you can pull out a calculator and start multiplying through by 4. I'm going to not do that here, and let's just skip this and come back to it in just a minute. Okay, so let's see if we can find the pattern to help us find A10. So I want to do something similar to what I did with the last example with the arithmetic sequences, and let's try to squeeze it in here again. So I have A1 is 2, A2 is 8, which we get by taking A1 and multiplying by 4. How do I get A3? Well, I take the previous term, so that was 2 times 4, and multiply by 4 again. That's going to be 2 times, what do I get when I have 4 times 4? I could rewrite that as 4 squared. How about A4? I'm going to take the previous term, which was 2 times 4 squared, and multiply that by 4. Do you remember your rules of exponents here? You can think of this as a 4 to the 1. So I get 2 times 4 cubed here. Whoops, if I want to keep going, I've got A5. I'm going to take A4, which is 2 times 4 cubed, and multiply that by 4. That gives me 2 times 4 to the 4th, and so on. So again, I want to look at what's happening here. The only thing that's changing is this exponent on the 4. And there's an understood exponent of 1 here. And I could think of the 2 as 2 times 4 to the power 0. 4 to the power 0 is just 1. All right, so what is the pattern here? Well, this exponent is always 1 less than the index of the term I'm at. Okay, so in general, an is going to be 2 times 4 to the power 1 less than n. We write that as n minus 1. Okay, so coming back to the second question, what is A10? See if I can squeeze it in here. A10 is 2 times 4 to the 10 minus 1, or 4 to the 9th. And that's going to be a really big number, so I'm just going to leave it like that for now. It's not too big. Let's just do it. I'm out of room. I'm going to slide it down here. 524,288. All right, so in general, we can do the same thing. So let's suppose we have a generic geometric sequence with common ratio r, and we want to come up with a formula for the nth term of the sequence. So I want to do the same sort of thing that we just did. So I've got my first term is A1. I get A2 by taking A1 times R. A3, we take A1 times R, that was A2, times R again. R times R is the same as R squared. To get A4, we're going to take the previous term and multiply by R again. That gives us A1 times R cubed. To get A5, I'm going to take A4, which was A1 times R cubed, and multiply that by R. And that simplifies to A1 times R to the 4th. Again, we see this pattern that the exponent on R is just 1 less than the index we're at. So an is going to be the first term, A1, times R to the power n minus 1. Again, this is a formula you'll need to memorize. All right, I want you to try to find the 32nd term of the geometric sequence with common ratio 2 and initial term A1 equals 1/2. So 2 here is my ratio, that's going to be R. Here's my A1 is 1/2. And this 32nd is telling me that n is 32. All right, I'm going to let you plug that into the formula in Canvas, and I'm going to move on to the next example. Let's try to find the first 4 terms of each sequence and then determine whether the sequences are arithmetic, geometric, or neither. And if we've got an arithmetic or a geometric sequence, let's give a formula. Okay, so we're going to start with the sequence an given by n squared plus 1. Okay, so a1, I'm going to plug in 1 for n. So I get 1 squared plus 1, which is 2. A2 is going to be 2 squared plus 1. That's 4 plus 1, or 5. A3 is going to be 3 squared plus 1. That's 9 plus 1, which is 10. And A4 is 4 squared plus 1. That's 16 plus 1, which is 17. Okay, so I look at this sequence. The sequence is 2, 5, 10, 17, and so on. Is this arithmetic? Well, if I go from one term to the next, do I get that just by adding a common difference? The answer here is no. If I go from 2 to 5, that's adding 3, but going from 5 to 10 is adding 5. So that's not the same number, right? So it's not arithmetic. Is it geometric? To determine if it's geometric, I want to ask, when I go from one term to the next, can I do that by multiplying by some constant? Well, to get from 2 to 5, I'd have to multiply by 5 halves. But to get from 5 to 10, I'd have to multiply by 2. So again, that's not the same number, right? So this is not geometric. So this sequence is neither geometric nor arithmetic. And we've already gotten the formula. Here's the formula for that sequence. All right, let's look at B. I've got the sequence 6, 12, 24, and so on. Okay, so the first thing I want to do is find the pattern, right? 6 to 12 and then 12 to 24. It looks like I'm multiplying by 2. And if I multiply by 2 to find each successive term, that is a geometric sequence. So this is geometric with r equal to 2 because I'm multiplying by 2. All right, I need to find the first 4 terms. I've got the first 3, so I need one more. I've got 6, 12, 24. I need to get the next term by multiplying by 2. That's going to be 48, and so on. How about C? 1, 1, 2, 3, 5, 8, and so on. Okay, so this is interesting. I've already got 4 terms, so I don't need to worry about finding any more terms. But what is the pattern here? If I add to get to the next term, well, going from 1 to 1 is adding 0. Going from 1 to 2 is adding 1. From 2 to 3, I'm adding 1. From 3 to 5, I'm adding 2, and so on. This isn't arithmetic. It's also not geometric. But this does have a special pattern. You might have heard the pattern as I was describing the addition to get to the next term. We're going to circle back to this example, so I'm going to just leave it like this for now, and in the next video, you'll see this one again. All right, my last sequence is the sequence given by an equals 3 to the power n. Okay, so a1 is going to be 3 to the power 1. a2 is 3 to the power 2, which is 9. A3 is 3 to the power 3, which is 27. And A4 is 3 to the power 4, which is 81. So my sequence looks like 3, 9, 27, 81, and so on. Is this sequence arithmetic or geometric? So you should ask yourself, can I get the next term in the sequence by always adding a single constant? If that's the case, then it's arithmetic. If I can get the next term by always multiplying by the same constant, then my sequence is geometric. In this case, we're going to have a geometric sequence with r, our common ratio is 3. I get each successive term by multiplying by 3. All right, we might also see sequences show up in word problems. So here's an example. A theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. The last row has 144 seats. How many rows are there in the theater? So if you think about your theater, you've got 20 seats here. The next row is going to have 20 plus 4. The next row has 20 plus 4 plus 4 again, and so on, all the way until I get to 144 seats. This is a sequence. It's an arithmetic sequence where I'm adding 4 each time. So this must be the nth term of the sequence. And I can, in fact, write down a formula for that nth term since I know A1, the first term is 20, plus n minus 1 times d. Here's my d. So d is 4. All right, so 144 equals 20 plus n minus 1 times 4. I just need to solve for n. Okay, and there you go. I've done that really quickly in the slide here. So we've plugged in to the formula here. I'm going to subtract 20 from both sides. That's how I get 124 on the left. And then I'm going to divide by 4 on both sides. That's where the 31 comes from. And finally, to solve for n, we need to add 1 to both sides. And so we get 32. That means that there are 32 rows in our theater.